The first thing you see is not the red desert, but a cloud. It hangs above the curved rim of Mars like a faint blue brushstroke, stretched along the line where night and day meet. From far away it looks delicate and harmless, a simple streak of vapor over a quiet planet. Beneath it, the surface is dark and ridged, scarred by old valleys and buried craters. Above it, the sky is so thin that at local noon on the highest plateau, the brighter stars would already be visible, shining through a daytime that barely deserves the name. Now imagine you are there, walking into that sky. Your boots sink a little into dust that behaves almost like smoke. Every step sends a small cloud around your ankles, grains of rust-colored powder that hang in the weak air and fall back in slow arcs. The slope is gentle, more like a long road that never quite levels out than a cliff. The horizon keeps its distance, as if it is being pulled away from you. You know, by the numbers, that you are climbing a mountain as wide as a small country. Yet your legs do not feel like they are on a mountain at all. The danger is not under your feet, it is above your head. With each meter of altitude, the pressure falls. What little air there is becomes even less. At the base, the atmosphere was already a thin veil, less than 1% of what you are used to at sea level on Earth. Up here, it drops to a fraction of that. If your suit fails, there is no time to gasp, no chance to take one deep breath and hold it. There is only instant boiling in your blood and fluid boiling away from your eyes. The sky that looked so empty is not just indifferent, it is actively hostile. What kind of world lets you stroll up a long, easy slope and quietly strips your lungs of air? We call that slope the side of Olympus Mons. We call that world Mars, a planet we often describe as dead. No global magnetic shield, no active plate tectonics on the surface, no widespread oceans of liquid water. Whatever heart once stirred at its core is now slow and muted. The evidence of ancient rivers is carved into the rock as frozen geometry, not flowing water. Dry deltas, cracked lake beds, sediments locked into stone. Yet the cloud above the limb is real, and it should not be so easy to explain. Mars has an atmosphere so thin that a human could not survive unprotected for more than a breath or two. Yet it still forms clouds, fogs, and storms. Dust devils twist across its plains like contactless tornadoes, lifting grains meters into the air. Entire hemispheres can vanish under a single global dust storm. In polar spring, sunlight reaches through sheets of carbon dioxide ice, warms the ground below, and jets of gas punch upward to spray dark fans of sand across the surface. High above, delicate clouds form out of water ice and carbon dioxide, often seeded on tiny grains of dust that came from beyond the planet itself. How can a world that lost its air still have weather? We could have ignored that question and kept Mars in the simple box marked dead. Instead, we wrapped the planet in a ring of patient instruments. Orbiters trace its gravity and magnetic field, photograph its canyons and dunes, taste its atmosphere at different heights. Landers crouch on the surface and listen for shallow quakes, measure pressure, temperature, and wind, and bake small samples of soil to see what evaporates. Together they form a watchtower, not a single stone tower on a hill, but a distributed ring of sentinels watching a sleeping giant. From that watchtower, the giant does not quite look asleep. The polar caps grow and shrink, not just with light and dark, but with subtle exchanges between ice and air. Frost coats dunes and then recedes. Some years the atmosphere swoons with planet-wide storms. Other years it keeps its dust mostly close to the ground. High clouds appear where they should not, made of water ice in a sky that we thought was too dry and too thin. Even the slow leak of gas into space continues as atoms are stripped away by the wind from the sun. In everyday language, Mars still breathes in its own slow, thin way. This is the paradox at the heart of our story. When we look at Mars with the naked eye, even through a telescope, it seems simple. A rusty ball, bright polar cap, occasional bright and dark patches that shift with the seasons. A world that has lost almost everything that makes Earth so comfortable. When we look with better instruments, The simplicity dissolves. We see traces of a past that included rivers, lakes, maybe even a northern ocean. We see a present that still has enough activity to redraw small parts of the landscape every year. If a planet can be mostly dead and still moving, what exactly do we mean by alive? You can feel the tug of that question in the way we talk about Mars. We do not send only one type of mission. We send climate orbiters that map the temperature of the atmosphere. We send landers that taste the soil near the poles. We send rovers that crawl through dried riverbeds and look for minerals that can only form in liquid water. Each device carries a small part of a larger set of questions. How much water was there? How long did it last? Where is it now? Could anything ever have lived there? Could anything still cling on in some isolated pocket? Behind those questions lies a more direct one that is easier to admit now than it was a century ago. Could we live there? The image of two humans climbing Olympus Mons is not just a poetic device. It is a test. Put a human body into that environment and ask what it would take to keep that body alive. You need a suit to hold pressure. You need warm layers to hold heat in the thin air. You need shielding from cosmic rays. Because the missing magnetic field and the missing thick atmosphere no longer blunt the storm of high-energy particles from space. You need water, food, and oxygen, and a way to get rid of carbon dioxide and waste. Every piece of that problem can be measured and weighed. For every kilogram of equipment you need on Mars, you must pay many kilograms of fuel launched from Earth. For every liter of water a person drinks, you must send it, recycle it, or make it locally. For every breath of oxygen, you must steal atoms from the Martian air or soil, or bring tanks from home. Suddenly, the cloud above the limb is not just beautiful. It is a hint. There is water ice in that atmosphere. There is carbon dioxide almost everywhere. There are ways to turn that thin sky into something useful if your machines are reliable and your calculations are right. This is where the watchtower image becomes more than just poetry. From orbit, we have already mapped where the planet is most generous with its buried ice. We know which slopes hold permanent frost, which craters contain layered deposits of frozen water and carbon dioxide, which regions have minerals that once formed in standing pools or flowing streams. We have measured the pressure and temperature profiles of the atmosphere and watched how they change over the course of a Martian year. We have recorded the size and timing of dust storms and seen how they alter the energy balance of the planet. The watchtower is drawing a map, and the map has two uses. One use is scientific. It tells us how a small rocky planet responds when its interior cools and its protective shields weaken. It gives us a sample of a climate that failed to stay in the comfortable zone and slid into a fragile, marginal state. The other use is practical. It tells us where we might safely land, where we might dig for ice, where we might place solar panels or nuclear reactors, where we might build the first modest shelter that deserves the name base. Why should these uses ever be separated? If we are honest, they cannot be. Any attempt to step on Mars physically will intertwine with the attempt to understand its history. Every footprint would be placed on layers of climate and geology that carry information about billions of years. Every landing site chosen for its engineering safety is also a sample site in a vast natural experiment the universe has already run for us. The dead planet is not just a destination, it is a data set with gravity. That leads us to yet another question, quieter but no less sharp. If Mars truly is a fossil of climate, a record of how a once more temperate world lost its air and surface water, can we really treat it as an empty canvas for our expansion? Or must we treat it as a kind of library? A place where the shelves are made of rocks and ice layers, where reading too roughly might erase the text. You might notice that none of these questions have clear answers. That is not a failure of science. It is a sign that we have reached the edge where data meets value. Instruments can tell us how thick the ice is at a given latitude. They can tell us the rate at which the atmosphere is leaking into space. They can tell us how old a particular volcanic plain might be. They cannot tell us whether it is wise to place a city there. In the background, another thread pulls at our attention. If water once flowed on Mars, even briefly, then chemistry had time to move. If lakes existed for thousands or millions of years, then cycles of freezing and thawing, evaporation and condensation, concentrated certain molecules in certain places. On Earth, similar cycles nurtured the earliest steps toward life. On Mars, we do not know what happened. It may be that nothing living ever emerged. It may be that something almost living appeared and vanished. It may be that some simple forms survived in pockets underground. How do we weigh the possibility of past or present life against the urge to turn a planet into a backup home? We stand at a strange place in history. We have just enough power to seriously plan a crewed mission to Mars, and just enough knowledge to know that the planet is not a simple blank slate. We can calculate how much fuel a fully reusable launch system might save. We can design habitats that recycle air and water with high efficiency. We can imagine greenhouses, drilling rigs, and factories that turn Martian air into rocket propellant. We can also imagine a scenario in which, in the act of solving the engineering problem, we contaminate or erase the very traces of Martian history that might have taught us something profound. This tension between curiosity and caution, between ambition and humility, is part of the hook that will carry us through the rest of this journey. We will not answer it quickly. Instead, we will unpack it piece by piece, starting from the sky and working down into the ground, then into the human plans that try to stitch the two together. If this opening raised new questions, like and subscribe to the Quiet Universe channel. In what follows, we will first treat Mars not as a symbol, but as a real world with a real atmosphere. We will learn how that thin sky is structured, how dust and ice share the high altitudes, how meteor smoke from space helps seed clouds, and how those clouds control temperature more than their delicate appearance suggests. We will watch how sunlight, gas, and fine particles combine to produce a climate that barely hangs together, yet still manages to sculpt the ground below. To understand why a dead world still has clouds, we now turn to the sky of dust and vapor that hangs above the Martian plains. At sunrise on Mars, light does not scatter the way it does on Earth. The horizon glows blue while the sky above it burns red. It is a reversal of what we are used to, caused by air so thin that only the smallest grains of dust and ice are left to play with sunlight. The air is nearly silent. There is no birdsong, no gusts that rattle leaves, only a constant whisper of particles carried by a reluctant wind. From orbit, the planet looks calm. From the ground, it behaves like a restless ghost. The air, though thin, moves with surprising energy. It can lift dust and carry it halfway around the planet. It can create waves that ripple through the atmosphere in patterns we still struggle to predict. These waves rise and fall, dragging dust and vapor with them, forming layers of mist that appear and vanish between dawn and dusk. When our landers look up, they see veils of brightness flickering across the sky. The key to this living sky lies in the smallest things. Tiny grains of meteor smoke drift through the atmosphere, leftovers from cosmic dust that burns as it enters from space. On Earth, these grains help form noctilucent clouds near the poles. On Mars, they may play the same role. Without them, ice crystals would find it hard to form. With them, the sky gains anchors, small seeds that let water vapor and carbon dioxide freeze into clouds even when the air is too dry for comfort. Think of it like this: a single speck of dust, lighter than a strand of hair, can gather a halo of ice around itself and become a mirror for sunlight. Billions of these floating mirrors drift high above the Martian ground, scattering light back into space and cooling the planet by several degrees. The difference may sound small, but on Mars, a shift of 10 degrees can change the boundaries of frost, the pattern of winds, and the very rhythm of its seasons. Why does this matter? Because those clouds rewrite the thermal map of the planet. When they reflect sunlight, the surface cools. When they trap infrared light, they warm the air above. The balance between those two effects decides where frost can survive the day and where it will sublimate into vapor. In the polar regions, the result is dramatic. Each year, The caps of carbon dioxide ice grow and retreat as the sun rises and falls. The thin clouds that ride over them act as both blankets and mirrors, shifting the timing of those cycles. Our models once failed to reproduce those cycles. They predicted temperatures too low, pressure too weak, an atmosphere that could not support such graceful motion. Then the data arrived from orbiters equipped with spectrometers and high-resolution cameras. They showed us something unexpected: high clouds forming where the models said none could exist. The puzzle forced us to rewrite the equations, to add the influence of dust grains, vertical mixing, and microphysics that we had ignored. When we did, the numbers began to match the reality. At its core, this is how science breathes. We build an idea, the world refuses to fit it, and we start again. On Mars, every false prediction becomes a clue. The persistence of clouds tells us the atmosphere is more complex than a simple layer of carbon dioxide. It holds traces of water vapor, faint, but enough to matter. It holds dust that acts as both poison and medicine for weather. Too much dust, and the planet chokes in a global storm that blocks sunlight for months. Too little, and the air becomes too clear to form the very clouds that modulate its temperature. Simply put, Mars lives in a delicate tension between clarity and opacity. When we zoom into the storms, the story grows more intricate. Dust storms on Mars begin like rumors. A patch of warm ground heats the air above it. The rising column creates a small whirlwind. The dust lifted by this whirlwind absorbs sunlight, it heating the air even more, which in turn lifts more dust. Within hours, the disturbance can grow from a local swirl to a continent-wide haze. The largest storms engulf half the planet, wrapping it in a veil that glows softly under the sun. In those weeks, the surface almost disappears. Rovers can barely see their own shadows. Solar panels gather less and less power until they shut down in the dark. But from space, the view is breathtaking. The storm becomes a living organism, pulsing with bands and waves. It radiates heat to space at night and traps it by day. When it finally settles, the dust drifts down unevenly, creating new patterns that future winds will trace again. Why it matters lines emerge naturally here. These storms show us that Mars still has a functioning climate engine, even if it runs on fumes. They also remind us that thin air is not harmless air. A world can be almost airless and still dangerous to technology and life. The dust grains are electrostatic, clinging to every surface. They scratch glass, foul joints, and hold chemicals that react with water and skin. In planning any future mission, human or robotic, we are forced to account for an atmosphere that both helps and hinders. When you picture that atmosphere, do not think of a blue dome. Think of a faint shimmer, a skin of gas stretched over a sleeping world, thin enough that sunlight passes through it unbroken. The air is mostly carbon dioxide, with traces of nitrogen, argon, and water vapor. It is clear most of the time, yet it can turn opaque in a single day. Its pressure changes slightly with each sunrise as ice at the poles evaporates, swelling the sky, then freezes again at night. Shrinking it, the entire planet breathes in and out with the rhythm of the seasons. To put it another way, Mars performs a slow inhale and exhale every year. Each breath moves trillions of tons of gas from one hemisphere to the other. On Earth, such swings would be catastrophic. On Mars, they are ordinary, part of the cycle that has persisted for millions of years. For all its fragility, this cycle gives Mars a kind of continuity. The same winds that sculpt dunes today likely sculpted them long ago. The same polar exchanges of gas and ice have carved layers into the caps like tree rings, each layer a record of the planet's climate. When we read those layers, we read time. They tell us when the atmosphere was thicker, when dust storms were stronger, when the tilt of the planet's axis changed and brought new extremes. At times, measurements suggest the temperature at certain altitudes rises higher than expected. It is as if waves of heat pulse through the thin air, carrying energy upward from the surface. These are gravity waves, invisible oscillations that ripple like the motion of a drum skin. On Earth, they shape weather patterns and air traffic routes. On Mars, they shape the movement of dust and ice crystals. They may even drive the formation of high-altitude clouds that reflect the sunrise in subtle colors. Why do we chase such faint signals? Because they are the language of a planet trying to tell us what it once was. If we can translate those signals, we can reconstruct how Mars cooled and dried, how its air escaped into space, and whether pockets of warmth might still exist beneath its surface. Each dataset is a sentence, each correction a new line in the story. In one famous sequence of images, we watched a tiny vortex whirl across the plain near a lander. The dust devil stretched hundreds of meters high, yet left the sky unchanged. It was a reminder that even a faint atmosphere can do complex work. The movement of dust changes how sunlight is absorbed, which changes temperature, which changes pressure, which in turn creates more movement. It is a feedback loop, fragile but persistent. Think of the planet as a clock with missing gears. The hands still move, but not at the same pace. Time here feels stretched. Storms rise and fade over months. Seasons last twice as long as ours. A year passes as the planet circles the sun in a wider orbit. The mechanisms of its weather are slow, but they are weather nonetheless. If we could stand beside one of the robotic sentinels now, we might see a faint halo of cloud glowing in the evening. We might feel the vibration of dust against our helmet as the wind changes direction. We might sense how the thin air presses almost nothing on our bodies, yet still carries enough power to reshape the surface grain by grain. The view would be beautiful and eerie, a silence filled with motion. From this silence, we learn humility. We learn that even a thin sky can teach us about persistence, about how energy flows in places nearly empty of air. It reminds us that habitability is not a single switch labeled yes or no. It is a spectrum. A world can hover at the edge of livability for ages, long after its oceans have gone. If you ask what makes Mars fascinating, it is not just the prospect of life, but the paradox of its endurance. It should have lost all movement long ago, yet every year we see fresh traces of weather. The thin sky continues to sculpt, cool, and whisper. The watchtower machines above it continue to listen, turning dust and vapor into data that fill our screens with color maps and graphs. Soon we will leave this sky and descend to the surface it hides. There, the patterns carved by rivers and frost tell another story, one written not in air, but in stone. We will follow that story to the maps of water that should not exist. When the dust clears and the satellites look down through the thinning air, a different Mars appears. It is not the planet of storms and vapors, but one of scars and channels. From orbit, the valleys stretch for hundreds of kilometers, etched into the crust with a precision that only flowing water can achieve. They wind and braid, merge and divide, then fade into deltas that spill onto the plains. Each one is a signature, a record written by a hand that has not moved for millions of years. At first glance, these channels look like dry riverbeds on Earth. Their curves match the same mathematical patterns. Their branching angles mirror the way liquid finds the easiest path downhill. Some are wide as major terrestrial rivers, with terraces and banks carved into stone. Others are narrow gullies that look recent, barely softened by erosion. The shapes are convincing enough that the first observers a century ago called them rivers without hesitation. They mapped them, labeled them, and dreamed of ancient oceans. The dream was not wrong, but it was incomplete. Mars did once have water, yet its story refuses to follow simple lines. Where the channels begin, there is often no clear source. Where they end, there is no consistent sink. Some cut through craters that should have been younger than the flows that made them. Others appear to begin in places that are too cold or too high for liquid water to have persisted. The evidence contradicts itself. To make sense of the map, we have to imagine a world that changed states many times, a planet of alternating awakenings and freezes. At its core, the puzzle begins with heat. The sun is weaker on Mars. The thin atmosphere barely traps warmth, even in its distant past. The surface should have been locked in permanent frost. Yet the channels show erosion that requires running water, not melting frost or vapor flows. Something, at some point, provided energy enough to thaw vast regions. Some models suggest volcanic outbursts. Others invoke impacts that release stored heat. A few combine both, proposing a cycle of brief warm periods triggered by chaos from within and without. In plain terms, the planet may have boiled in pulses rather than basked in long summers. If that is true, then each valley we see from orbit marks not a single river, but an episode. A sudden thaw carved it, a freeze preserved it, and another thaw partly reshaped it. The global map becomes a diary of events, not a stable coastline. When we trace it, we read interruptions more than continuity. The largest feature in this diary is an imagined ocean that once may have covered the northern plains. It would have stretched from the equator to the pole, shallow by Earth's standards, deep enough to hold all of Mars's known ice several times over. The shorelines drawn from orbital data seem persuasive gentle slopes, terraces, and sediment fans that look like beaches. But when topography improved, the neat picture broke down. The supposed sea level is not level at all. It rises and falls with the ancient crust, as if the ground itself warped long after the water was gone. Why would a sea tilt unless the planet's axis or mass balance changed? If the poles wandered, or if enormous volcanoes rose after the ocean vanished, the crust could have shifted. In that case, the evidence of a single global sea might be misleading, a mirage created by moving land rather than moving water. The idea is not comforting. It means our maps can lie even when the data are accurate. To put it another way, we are drawing a portrait of a ghost while the canvas itself is stretching under our hands. Yet even if the ancient ocean never existed in the way we imagine, the smaller lakes did. Orbiters have found layered deposits inside craters that once held water. The layers tell of calm conditions, sediment settling over years rather than hours. The minerals inside those layers bear the fingerprints of standing water. Clays, sulfates, and carbonates form only when water lingers. Each crater lake, preserved in stone, becomes a time capsule. If we could step into one of those basins today, we would see steep walls streaked with lighter bands where water levels once stood. The floor would be a flat expanse of dust hiding the chemical remains of past water. In some cases, the edges show channels leading inward and outward, inlet and outlet frozen in place. The symmetry is too precise to be coincidence. The planet did not imagine these shapes. It lived them. Why does this matter to us? Because each lake is a clue to the conditions under which life could once have started. A shallow, long-lived pool offers a natural laboratory for chemistry. Freeze and thaw cycles concentrate molecules, just as Earth's early ponds did. The presence of such basins on Mars means that the ingredients and processes for life were at least possible, if not inevitable. The question shifts from, could it happen, to how often did it fail before something took hold? When we examine these sites with modern spectrometers, we find another surprise. Some minerals form not in neutral water but in acidic or saline conditions. They suggest that the lakes were harsh, perhaps briny, perhaps short-lived. They could have supported chemistry, but not comfort. This paints Mars not as a paradise lost, but as a world that flirted with habitability and then recoiled. What could make a planet so ambivalent? Part of the answer lies in its size. Mars is smaller than Earth, only about half its diameter. It cooled faster, lost its internal heat, and with it the magnetic field that once protected its air. The solar wind stripped the atmosphere over time, reducing the pressure and letting the remaining water escape into space or freeze underground. A few billion years ago, the planet still had enough air to support rivers. A billion years later, it had barely any at all. We see the record of that loss in the maps of its valleys. In younger terrain, the channels are shallow and scattered. In older terrain, they are deeper and denser. The pattern reveals decline. Each generation of valleys carried less water for shorter periods. Eventually, the flow ended. The last trickles froze in place, and wind took over as the sculptor of landscapes. Simply put, the maps show both the rise and the funeral of water. If we overlay these maps with mineral surveys, the correlation is striking. The regions richest in hydrated minerals align with the densest networks of valleys. That is no coincidence. Where water stayed longest, it altered the rock most deeply. The chemistry confirms what the topography implies. Water was not everywhere at once. It migrated, followed by the changing sun and the planet's shifting tilt. Mars wobbles over time, swinging its poles toward and away from sunlight. Each wobble changes the stability of ice, moving the zones of melting and freezing. Over millions of years, these cycles carved new drainage paths and buried old ones under dust. The result is a planet whose memory of water is fragmented, like torn pages from a book. Scientists reconstruct the story by comparing craters, layering ages, and modeling ancient climates. The challenge is immense. Even the most detailed data remain incomplete, and each interpretation carries uncertainty. Some argue that the channels could form from sudden floods of melting ground ice, brief and violent, rather than steady streams. Others see evidence for rainfall, implying a thicker, warmer atmosphere. Both explanations fit parts of the map. Neither fits all. Why do we care so much about reconciling these fragments? Because water is the thread that ties geology to biology. It is the solvent of life, the medium that carries heat, minerals, and chemical reactions. If we can understand how long liquid water survived on Mars, we can estimate how long the window for life remained open. Each contour on the map is not just a line of erosion, it is a potential timeline for evolution that might have been. The idea that water once flowed where today the air would boil it away feels almost like a contradiction. Yet that contradiction is the heart of discovery. It tells us that planetary climates are not static. They can swing from warm to frozen, from thick air to near vacuum. The maps of Mars are warnings in stone about how fragile stability can be. In everyday language, Mars teaches us that a world can look permanent while quietly losing what made it alive. Imagine now the explorers of the future, standing where the ancient rivers met the sea that may never have been. They will look at smooth plains that stretch to the horizon, at dunes that hide layers of salt and clay, and they will wonder how to prove the presence of an ocean that may have left no trace except chemical whispers. They will bring drills and spectrometers, perhaps melt a little ice, perhaps release trapped gases. Every sample will add a pixel to the picture we began from orbit. These future maps will not just trace where water was. They will trace where it can be found again, buried as ice or locked in minerals. For mission planners, that is as important as the story of the past. Ice is not only evidence, it is resource. It can become air, fuel, and drinking water. The maps of vanished rivers become guides for survival. The ghost of the old sea becomes a supply chart. Here, science and ambition meet. To study a world deeply is also to prepare to inhabit it. The same data that reveal lost lakes will one day tell a crew where to dig for ice. The same chemistry that proves ancient brine will help engineers decide how to extract oxygen. The boundary between exploration and colonization is thinner than the air above the plains. Why it matters becomes personal. Understanding the hydrology of Mars is not just about the past, it is about the ethics of the future. If life once existed there, however simple, we must ask what right we have to alter its remnants. If no life ever appeared, then the planet becomes an empty canvas, and the moral weight shifts. Every discovery of water blurs the line between these outcomes. If we read the maps carefully, we see both hope and caution. The hope is that water, the universal solvent, connects us to another world. The caution is that water does not guarantee comfort or safety. It can also mark the boundaries of extinction. As the light fades on the northern plains, the old shorelines vanish into shadow. The sensors above them continue to scan, translating ghostly reflections into data streams. On Earth, the numbers resolve into images of color-coded minerals, into blue and brown maps labeled with long Latin names. They are beautiful, but they whisper a reminder. Beauty in science is often the residue of loss. Soon, we will move from these frozen deltas to the engines of ice and sand that still shape the planet's surface today. The story of water does not end in stone. It continues in the strange behavior of carbon dioxide and frost that erupts each spring. So we follow the thaw to the engines of ice and sand. Each spring on Mars, the planet exhales. The sound is inaudible, but its mark is visible from orbit as thousands of dark streaks spreading across the southern plains. The season begins in silence, with the polar cap gleaming white under a sun that hangs low in a salmon-colored sky. As the light grows stronger, it passes through layers of carbon dioxide ice that are clear as glass. The ground beneath absorbs the warmth first. A thin film of gas forms, trapped between rock and ice until the pressure builds enough to punch through. Jets burst upward, flinging dust and sand in tall fountains. From above, they look like ink stains bleeding through paper. This is the strange weather of a world that forgot how to rain. The ice that fuels it is carbon dioxide, the same gas we exhale with every breath. On Earth, it exists only in frozen warehouses and laboratories. On Mars, it covers millions of square kilometers each winter, then vanishes in a storm of sublimation. Where the jets erupt, they carve pits that widen over time. Each year, the pattern repeats, and the surface develops a network of dark veins that scientists call spiders. They are not alive, yet they behave like something that grows. Each spring, the spiders branch and spread, linking old vents to new ones. The process is mechanical, driven by sunlight, pressure, and gas. But the result is haunting. The landscape appears to crawl, reshaping itself with every season. The spiders are the planet's pulse, a reminder that its surface is not dead rock but an engine that still turns. To put it another way, the Martian ground breathes through its skin. The mechanics of this breathing are delicate. The transparent slabs of carbon dioxide ice act like greenhouse panes, trapping heat beneath them. When the gas escapes, it carries dust and sand upward through holes and cracks, spraying them across the ice. Some of the material falls back, darkening the surface and increasing absorption of sunlight. The feedback accelerates the melting and creates more jets. Over a few weeks, the white cap becomes streaked with black fans that trace the direction of the wind. The process ends when the ice is gone and the ground warms enough to remain bare until autumn returns. These seasonal eruptions tell us two important things. First, Mars still exchanges energy between its surface and atmosphere in complex ways. Second, the planet remains dynamic on a timescale we can observe. The same regions have been photographed year after year, showing changes in shape, color, and brightness. The map of Mars is not frozen. It is a living record. In everyday language, the ice moves and the ground answers. Closer to the equator, where sunlight is stronger, another engine works. This one relies on water ice mixed with dust. When buried ice slowly evaporates, it destabilizes the soil above. Slopes collapse, forming fresh gullies that look uncannily like those made by streams on Earth. For years, scientists debated whether liquid water was responsible. The answer now appears more complex. Many gullies form when sublimating ice triggers landslides, not when liquid flows. Yet in some cases, briny water may still seep briefly before freezing. Why does this distinction matter? Because every mechanism of motion on Mars doubles as a clue to its habitability. Where ice turns to gas, we find energy gradients. Where gas carries dust, we find transport of materials. These are the basic ingredients of geology and, indirectly, of chemistry that could support life. Even in an environment too cold and dry for biology as we know it, physical engines can create pockets where temperature and moisture briefly align. Imagine a plane covered by frost, silent except for the hiss of escaping gas. The sun glances off the ice, the surface darkens, and the air shivers. A shadow moves, but it is not alive. It is the ghost of movement itself. Dust and vapor rising in the same motion that built dunes and carved gullies over millennia. The planet acts as both sculptor and subject. Why? It matters becomes clear in this image. Mars shows us that erosion does not need rain, and transformation does not need time measured in ages. A small shift in sunlight, a thin film of gas, can redraw the surface in a single season. It changes how we think about planetary evolution. Worlds need not be geologically dead to appear calm. Activity can hide in frost, repeating endlessly under the same thin sky. The physics of this seasonal engine have been tested in laboratory chambers on Earth. Under Martian pressures and temperatures, carbon dioxide behaves in strange ways. It can flow under its own vapor, slide across surfaces, and even cause grains of sand to vibrate and rearrange. Researchers have recreated small spiders by placing clear ice over dark soil, then shining a lamp to mimic the sun. The results match what orbiters see. The shapes form in hours, not centuries. Simply put, the Martian spring is a slow explosion repeated every year. There is beauty in this repetition. The planet cycles between white silence and dark motion, then back again. Each cycle transfers energy upward, stirring the air and feeding the thin atmosphere with dust. That dust becomes the nucleus of new clouds, closing the loop. What begins as frost ends as weather. The planet's climate is built on these feedbacks. Small causes multiplied across a whole hemisphere. When we look at Mars in this way, its surface becomes an archive of physical laws in motion. Dunes migrate, craters fill, and slopes erode not from rivers but from frost. Even the smooth plains that we once assumed to be ancient lava may partly owe their texture to repeated seasons of sublimation and deposition. Every grain of sand has traveled countless times between ground and sky. In some polar regions, thin sheets of ice cover dunes that sing. When the frost layer collapses, the grains slip and vibrate, producing low-frequency tones that instruments can detect. It is a world that hums to itself through physics alone. These natural songs tell us about the size of the grains, the depth of the ice, and the temperature of the air. They are data disguised as music. Why does this matter beyond curiosity? Because understanding these small engines helps us predict how Mars will behave when we send machines or people there. Rovers can be trapped in dust that behaves like fluid. Landers can lose power under sudden snowfalls of carbon dioxide crystals. Human explorers will have to read the rhythm of the seasons to avoid landing during storms or freezes. The more we learn about these patterns, the less alien the planet becomes, though it never loses its strangeness. To put it another way, every machine we send to Mars must learn to breathe with it. The concept of planetary breathing may sound poetic, but it is measurable. Instruments have recorded annual fluctuations in atmospheric pressure as the caps grow and shrink. The total mass of the atmosphere changes by about a third each year. No other planet we know shows such a dramatic cycle. The air literally moves from pole to pole, taking with it traces of dust and gases. Over time, this breathing may even shift isotopes, leaving subtle fingerprints that reveal the history of the planet's atmosphere. Beneath the surface, the same gases may carve cavities and channels. Radar measurements hint at voids where ice once sat. Some may be traps for residual gases or reservoirs of ancient frost. If we ever drill into these layers, we might find preserved records of Mars's earlier climate locked inside. Each meter down is a deeper look into time. In everyday language, the spiders, the dunes, and the frost vents are all pages of the same book, written by pressure and light instead of ink. When viewed over decades, the changes in the polar regions tell a slow story of erosion and renewal. Some areas gain ice, others lose it. The balance shifts with the tilt of the planet's axis and with subtle variations in sunlight caused by its elliptical orbit. Mars wobbles like a top, changing the amount of light each pole receives. Over tens of thousands of years, these oscillations redistribute the frost, building new caps and erasing old ones. The cycles may drive periods of temporary thickening of the atmosphere when more carbon dioxide is in the air and less is locked in ice. Why? It matters continues here. Such cycles could create windows of relative warmth and pressure, long enough for water ice to melt briefly or for chemical reactions to proceed faster. Life, if it ever existed, might have adapted to these rhythms, sleeping through the dry ages and stirring when the air grew heavy again. The engines of ice and sand are not just geological curiosities. They are the heartbeat of a climate that may once have supported biology in fleeting bursts. If we step back, the planet becomes a system of self-regulation at the edge of collapse. It never reaches equilibrium, yet it never stops trying. Each season it rebalances its thin atmosphere, moves its dust, redistributes its frost. The dance is fragile but persistent. It is a kind of resilience without consciousness. Why do we keep returning to this idea of breathing and heartbeat? Because it humanizes what would otherwise be numbers. We recognize in Mars the same pattern we rely on ourselves. A cycle of intake and release, tension and relief. It is a pattern that signals life on our planet. Seeing it echoed in stone and frost elsewhere reminds us that the boundary between living and non-living is thinner than we once thought. The next step in our journey is to test this resilience against human limits. We have seen the atmosphere, the rivers, and the engines of frost. Now we will climb to the heights where these processes meet the sky, to a mountain so large it curves with the planet itself. Its summit reaches into the upper air where stars shine at noon. There, the lessons of wind and ice meet the realities of human endurance. So we set our path toward the walk up a mountain the size of France. Imagine a mountain so large that its slopes fade into the curve of a planet. From orbit, it looks almost gentle, a wide ripple frozen in rust-colored stone. Yet that ripple is Olympus Mons, the tallest volcano in the solar system, rising nearly 25 kilometers from base to summit. It dwarfs every peak on Earth. If you placed Everest on its side, it would barely cover a fraction of its base. The mountain stretches wider than France, so large that the edge of its plateau disappears beyond the horizon before you have even started to climb. Climbing Olympus Mons would not feel like climbing a mountain at all. For most of the journey, the slope is only a few degrees. You would walk for hundreds of kilometers, slowly ascending, hardly noticing the change in height. The ground beneath your boots would be packed dust and basaltic rock, cracked by time and peppered with small stones that shimmer under weak sunlight. Above you, the sky would fade from salmon to black as the atmosphere thins. By the time you reached the caldera rim, stars would shine even in midday. In plain terms, the mountain is so big that it has its own weather and gravity quirks. Mars's thin air cannot carry moisture the way Earth's does. But Olympus Mons still creates patterns of wind. Air cools as it rises up the slope, then warms again as it descends the other side. Clouds form near dawn and vanish by afternoon. The low pressure at the summit draws gases upward, adding to the planet's slow breath. If you stood halfway up, you could feel the wind change direction without seeing a single cloud. It would be like standing inside an invisible tide. The climb, though gentle in angle, is brutal in environment. The air pressure at the base is already less than 1% of Earth's. Near the summit, it drops to a fraction of that. Breathing unassisted would be impossible. You would wear a pressure suit thicker than any mountaineer's gear, carrying tanks of oxygen, filters for carbon dioxide, and layers of insulation. Every movement would be slow, measured, a balance between conserving energy and maintaining warmth. Radiation levels would rise with altitude because the thin atmosphere above offers little protection. Why does this mountain matter so much to us? Because it encapsulates the scale of Mars, both in physical and symbolic terms. Olympus Mons is a monument to time, It formed over millions of years as lava poured from vents that stayed open longer than any on Earth. The planet's crust never broke into moving plates, so the volcano could build upward in the same place endlessly. The result is a structure so vast that its base curves with the planet itself. Think of it like this. Earth's volcanoes are wounds that heal quickly. Mars's are scars that never close. Each layer of Olympus Mons is a page in the planet's geological diary. The oldest flows near the base tell of an age when Mars still had a thicker atmosphere and perhaps even water. The younger layers record drier, colder times. Some parts of the mountain are dusted with frost each winter, the last remnants of a global system that once cycled water freely. From orbit, bright streaks appear and fade seasonally, hinting that even now sublimation reshapes the slopes. Why? It matters becomes clear as we trace these patterns. The mountain is not just a relic. It is a reference point for how the planet changed. Its massive bulk influenced local climate, diverting winds, altering storm tracks, and trapping dust. Understanding Olympus Mons means understanding how Mars breathes and cools. The volcano's size alone challenges our models of planetary heat loss. A world that can build such a mountain is not as inert as it seems. For explorers, the mountain offers both promise and peril. Its vast shield provides a smooth landing zone, free of large boulders and deep canyons. The slopes are predictable, the terrain stable, yet the thin air and high radiation make survival difficult. Solar power weakens with altitude because dust and atmosphere scatter less light. Batteries discharge faster in cold. Communication with orbiters lags. When the mountain's curvature blocks the line of sight, each of these challenges is solvable, but together they remind us how alien even familiar geology becomes under another sky. Imagine standing at the base, looking up at a horizon that never seems to climb. The ground tilts slightly, then disappears into a hazy red distance. You begin walking. Days pass. The angle never changes much, but the pressure in your suit gauge drops steadily. The sky grows darker. At night, you see the faint outline of Phobos racing overhead, its shadow slicing across the plain. The planet's stillness seeps into you. Every sound feels swallowed. You are climbing not a mountain, but the idea of persistence itself. Halfway up, you might encounter cliffs and lava terraces that mark old eruptions. Some rise 6 kilometers from base to rim, walls of stone that dwarf any canyon on Earth. The caldera at the top is a cluster of overlapping craters, each one a record of a new pulse of magma that once forced its way upward. Inside those craters, the ground lies flat and cracked, a field of frozen flow patterns. If you could touch it, it would feel like glass coated in dust. The cold is so deep that even carbon dioxide can condense in shaded corners. Simply put, Olympus Mons is both tomb and telescope. Its layers preserve the memory of a planet that was once warm enough to flow, while its height lets us peer into a sky almost free of air. If a person could survive at the summit, the view would be unlike any other. The curvature of Mars would be obvious. The horizon would appear bowed downward, and the sun would rise and set slowly. Distorted by the thin air, the colors would shift from copper to violet. Shadows would stretch impossibly far. At noon, stars would be visible, faint points above a small, pale sun. To look outward from there would be to see space itself pressing close. Why climb it then? Knowing the risk. Because Olympus Mons offers something beyond geology. It offers perspective. On Earth, mountains are where we measure our endurance. On Mars, a mountain this size becomes a test of meaning. The climb is a symbol of human curiosity taken to its extreme. Each meter upward is a statement that we are willing to meet nature on its own scale, even if the air itself refuses to join us. In everyday language, climbing Olympus Mons is like walking across a continent only to arrive at the sky. From a scientific view, The mountain also holds secrets about the interior of Mars. The weight of Olympus Mons presses down on the crust, bending it. By studying this depression, scientists can estimate the planet's rigidity and the depth of its lithosphere. The numbers suggest that the crust beneath is thicker and cooler than Earth's, which explains the absence of plate movement. Yet traces of residual heat may still rise from below, keeping some regions of the mantle semi-molten. Olympus Mons may be extinct, but its presence hints at lingering energy deep inside. This possibility links the mountain to Marsquakes detected by seismometers elsewhere. Each tremor could be the echo of that internal struggle, the last motions of a cooling world. If we can connect those signals to the mountain's mass and shape, we can map the hidden layers beneath the surface. In this sense, Olympus Mons is both the largest mountain and the largest experiment ever run on Mars. Why? It matters extends beyond science. To climb this mountain, even conceptually, forces us to confront scale. Our lungs, our hearts, our tools are built for a narrow range of conditions. On Mars, that range collapses. Every breath becomes an act of engineering. Every step, a calculation of survival. The sheer immensity of Olympus Mons humbles ambition. It reminds us that exploration is not conquest but conversation, and that some conversations must begin with silence. If you imagine two astronauts standing on the rim at sunset, their visors reflecting the distant glow of Earth, you can almost feel the pull of that silence. They are not just explorers, they are messengers between worlds, witnessing what happens when persistence meets emptiness. They would know that the mountain beneath their boots took millions of years to rise, and that their presence will vanish in seconds compared to that timescale. Yet they would also know that data from their suits and instruments will ripple across space, returning to the planet that built them. At its peak, Olympus Mons ceases to be a place and becomes a mirror. In the mirror, we see both our smallness and our reach. The climb ends in a question rather than a victory. What does it mean to stand on the highest point of a dead planet and still feel alive? The answer lies not in altitude, but in awareness. Mars, through its vast mountain, invites us to measure our resilience not by what we conquer, but by what we endure. If the mountain teaches anything, it is that endurance is a kind of dialogue between matter and will. The rock endures through time, we endure through meaning. The bridge between them is curiosity. As the explorers turn away from the edge and begin their descent, the world below glows faintly in twilight. Far to the west, dust storms roll across the plain like slow waves. Somewhere beneath them lies the site where another machine once tasted Martian water. To understand how close we already are to touching that ancient element, we now follow the story of the day we tasted Martian water. It began with a scoop of soil. A robotic arm extended over a plain of pale red dust, paused, and then pressed its metal claw into the ground. The arm belonged to the Phoenix lander, a machine built to answer one question that had haunted us since we first mapped the planet's dry riverbeds. Is there still water on Mars? Even in the smallest amount. The scoop scraped once, twice, and lifted. The grains it carried looked like dry powder under the sun, but they behaved strangely. Some clumped together, sticking to the edges of the instrument as if touched by moisture. Under the microscope, they shimmered faintly, hinting at crystals hidden within. Scientists on Earth watched the feed with quiet awe. For years, we had dreamed of finding a sign, and here it was, in the shape of mud that refused to act like dust. In plain terms, we had just scratched the surface of another world and found frost hiding underneath. The lander's next task was to heat the sample. It dropped a pinch of soil into a small oven no larger than a thimble. The instrument sealed, warmed, and waited. When the temperature reached 0 degrees Celsius, sensors detected vapor. It was water, released as the ice in the soil melted and boiled away. The proof was undeniable. Mars had not only once contained water, it still did, right there beneath the surface. Why? It matters reveals itself instantly. That moment changed our view of the planet forever. Until then, we thought of Mars as bone dry, a place where all moisture had escaped to space. Phoenix showed that the planet had kept part of its inheritance frozen just below the dust. The discovery meant that liquid water might appear again, however briefly, under the right conditions. It also meant that any plan to explore or live there would have access to the most essential resource. Imagine standing beside that machine as it worked. The air is so thin that sound barely travels, but you would feel the vibration through the metal frame, inside the oven. Ancient ice from a time when Mars had rivers and clouds was turning back into vapor for the first time in millions of years. You could not smell it through your helmet, but you could imagine the faint scent of hot dust and salt. The planet was giving up one of its oldest secrets, 1 teaspoon at a time. The Phoenix lander also carried a small chemistry lab called TEGA. It was designed to identify salts, minerals, and other compounds that tell stories about water's history. What it found was even stranger than expected. Mixed in with the ice were perchlorates, salts that can draw water from the air and lower its freezing point. On Earth, these chemicals occur in deserts and can keep liquid water stable even when temperatures fall far below freezing. Their presence on Mars suggested that briny films might form at dawn and dusk, enough to let some reactions continue in the cold. To put it another way, Mars cheats its own cold by making antifreeze in the dirt. Why do these traces matter to us now? Because water is more than a drink. It is a medium for chemistry. Every reaction that built life on Earth began in water. Finding any version of it elsewhere, even mixed with salts, expands the boundary of the possible. The Phoenix results hinted that the difference between lifeless and living worlds might not be as vast as we thought. It could come down to temperature, chemistry, and timing. The day Phoenix tasted water was not the first time we suspected it was there. Decades earlier, orbiters had mapped hydrogen signatures near the poles, suggesting hidden ice. Landers had seen frost that came and went with the seasons, but Phoenix gave the first direct, measurable proof. It turned suspicion into evidence. In everyday language, the robot touched the ground, and the ground answered. After the oven tests, the lander performed another experiment. It exposed a patch of soil by removing the top layer of dust, then waited. Over the next few days, cameras watched the freshly exposed surface. Bright flecks appeared and then shrank, as if evaporating. Those flecks were ice sublimating directly into vapor under the thin air. It was a natural process, happening slowly enough for us to witness from millions of kilometers away. For the first time in human history, we saw water changing state on another world. Why it matters deepens here. The simple act of ice turning to vapor connects Mars to Earth in a tangible way. It proves that the same physics governs both planets, despite their differences. The universality of that process, the way sunlight and pressure interact, reminds us that nature repeats its patterns everywhere. It also means that where there is ice, there might once have been rain, lakes, or oceans, and perhaps, if conditions allow, there could be them again. Phoenix was not alone for long. Years later, the Curiosity rover discovered evidence of ancient lake beds in Gale Crater. It drilled into rocks that had once been mud and found minerals shaped by long contact with liquid water. Opportunity and Spirit had already seen hematite nodules and etched surfaces that spoke of wet histories. Each mission added another piece to the puzzle. Taken together, the evidence showed that water had not just visited Mars briefly, it had shaped it. Simply put, the red planet once knew how to flow. The discoveries also forced us to reconsider our definitions. For life to exist, we usually demand stability liquid water for millions of years, a steady climate, protection from radiation. Mars may never have offered all those comforts at once. Yet even brief episodes of habitability, repeated over ages, could have allowed simple chemistry to take root. If life began, it might have adapted to cycles of freeze and thaw, hiding in the soil when the surface froze, waking when the temperature rose. This idea is not fantasy. It is logic drawn from resilience we see on Earth: microbes in Antarctic ice, spores in deserts, and bacteria that thrive in salt all show how life adjusts. The lesson is that fragility and persistence can coexist. Mars could have followed the same rule in its own way. The instruments on Phoenix were not meant to detect life directly. They were designed to learn the planet's chemistry, to tell us whether the soil was acidic or alkaline, whether it could support reactions familiar to biology. The results were mixed. Some readings suggested nutrients. Others revealed oxidizing compounds that would destroy organic molecules. The soil was both fertile and toxic, a paradox we still struggle to explain. It was as if Mars had prepared the table but never served the meal. Why does this paradox fascinate us? Because it mirrors our own uncertainty about what we are searching for. When we look for life elsewhere, we are also testing the limits of our definition of life itself. Mars challenges us to imagine existence that might not look like us, that might breathe chemicals instead of air, that might live at speeds or scales we would not notice. Every grain of soil tested by Phoenix becomes a question mark pressed against our assumptions. To put it another way, we are not just exploring Mars, we are testing our own imagination. The data from Phoenix continue to echo through later missions. Perseverance, currently exploring Jezero Crater, carries instruments that owe their design to those early lessons. It looks for carbon compounds with better tools and stores samples for eventual return to Earth. Those samples may tell us if the story of Martian water includes a biological chapter. The process is slow and careful because one discovery can reshape not only science but philosophy. If future analyses find even one preserved cell, one microfossil, or one pattern that cannot form without biology, it will mean that life is not a singular event but a common outcome. The implications would reach far beyond Mars. It would tell us that the conditions for life are not rare miracles, but normal results of chemistry wherever water and energy meet. Yet even if we find nothing alive or fossilized, the impact of the Phoenix experiment remains profound. The act of heating that scoop of soil, of watching vapor rise, was a rehearsal for all future missions. It proved that delicate measurements are possible on another planet. It taught us how to build machines that can analyze and survive in alien cold. It showed that discovery is not a sudden revelation but a chain of persistence, much like the climb up Olympus Mons itself. Why it matters ends where it began, with humility. The day we tasted Martian water reminded us that exploration is not conquest, it is listening. Phoenix listened to the soil and heard a whisper we had waited generations to hear. The whisper said, "I still remember being wet." From that whisper came a new direction for exploration. The next step was to map where this hidden water rests, how it moves with the seasons, and what it means for the thin atmosphere above. The orbiters became our cartographers in the sky, measuring frost and vapor, tracing the planet's invisible tides. The machines began to see Mars not just as land, but as a system that connects sky, ground, and deep ice. That transition marks the bridge to our next story. If Phoenix showed us the taste of water, the watchers in orbit will show us the full map. So we now rise above the surface to join the cartographers above. High above Mars, a fleet of silent machines traces the planet's every contour. Each one follows a path so precise that the same crater passes beneath its sensors at nearly the same second every day. Together they form a network of eyes and instruments, an orchestra of orbiters tuned to the faint rhythms of a world that still stirs beneath its frozen skin. From these watchtowers, the story of Martian water and air becomes a global narrative. The first task of these cartographers is simple in principle: to map. Yet mapping a planet is not just drawing its surface. It is revealing how light and heat move across it, how dust rises and settles, how ice migrates from pole to pole. The data arrive as columns of numbers, transformed into maps of color and texture that reveal what no human eye could see from the ground. Each pixel is a measurement of reflected sunlight or thermal radiation. Each track is a line in a planetary diary. When the Mars Reconnaissance Orbiter began sending back its images, The scale of detail startled even the scientists who designed it. Boulders the size of cars, ripples of dunes, cracks within cracks. Each image carried the precision of a low-flying aircraft. Yet from hundreds of kilometers away, in those pictures, frost crept down crater walls. Dust devils left looping trails on plains that looked untouched. Every scene contradicted the idea of a still world. In plain terms, the orbiters discovered motion where we expected silence. They also found balance where we expected chaos. Each Martian year, the poles grow and shrink with the seasons. But the total mass of ice remains roughly constant. The carbon dioxide that freezes in winter returns to the air in spring. Water ice shifts more slowly, seeping through dust and rock. The cycle is stable yet alive. Orbiters equipped with radar can see several meters below the surface, revealing hidden layers of ice that hold the climate history of millions of years. Each layer is a bookmark in time, a record of how the planet leaned toward or away from the sun, how its tilt changed, how its atmosphere thickened or thinned. Why does this matter? Because those layers are the only surviving climate archive of another terrestrial planet. On Earth, plate tectonics and erosion erase ancient weather. On Mars, the memory remains intact, stacked in ice like a library of seasons. To read that library is to learn how a world can shift from wet to dry and from active to dormant without ceasing to breathe. Above the polar regions, another cartographer circles endlessly the Mars Odyssey orbiter. Its instruments sense the faint radiation emitted by hydrogen, a proxy for water. By comparing readings across latitudes, scientists built the first global map of near-surface ice. It showed that hydrogen and therefore water lies buried almost everywhere beyond 30 degrees latitude, even near the equator. Small pockets appear. These findings rewrote our expectations. Ice is not confined to the poles. It is the planet's hidden skeleton, a ghost ocean locked beneath dust. Simply put, the desert hides glaciers. From this discovery emerged a new line of inquiry. How stable is that hidden ice? If the planet's tilt or orbit changes, will the ice migrate, melting slightly, refreezing elsewhere? Data from orbit show traces of this migration in subtle shifts of the terrain. Frost deposits appear in new places, then vanish. Ridges thought to be ancient may in fact be fresh, carved by slow flows of buried ice. Mars continues to sculpt itself in a language of sublimation and sediment, and the orbiters act as translators. The Mars Atmosphere and Volatile Evolution mission, often shortened to MAVEN, joined the orchestra later. Instead of mapping the surface, it watches the sky. MAVEN's sensors track how the upper atmosphere leaks into space. The solar wind, unfiltered by a magnetic field, strips away atoms one by one. Over time, this steady loss transformed Mars from a thicker, wetter world to the thin air we see today. By measuring the rate of escape, MAVEN helps us calculate how much atmosphere has vanished and how fast the process continues. Why it matters unfolds here. Without MAVEN, we would still think of the missing air as a mystery. Now we see it as a steady process, one that may still be reshaping the planet. The same sunlight that drives sublimation on the ground also drives escape in the sky. Energy flows upward, taking atoms of oxygen and hydrogen with it. What we call the cold silence of space is, in truth, a slow wind of matter leaving forever. To put it another way, Mars is still exhaling, and we are catching its breath. The orbiters also listen for electricity. When solar storms strike, they create auroras over the poles, faint veils of ultraviolet light invisible to the human eye, but bright to detectors. These auroras mark where the sun's magnetic field touches the remnants of Mars's own. They show us a planet in constant dialogue with its star. Even without a global magnetosphere, Mars can still glow with polar lights, its thin air conducting energy along ancient lines of force. Why? It matters deepens again. Those lights reveal that space weather can affect a planet's climate. Solar storms alter the rate of atmospheric escape. changing how quickly gases are lost. They can also energize particles that penetrate to lower altitudes, influencing chemistry in the upper air. Studying this interplay helps us understand not just Mars, but Earth, reminding us that our magnetic shield is both precious and fragile. Every instrument in orbit tells a different part of the same story. Cameras map the visible surface. Spectrometers analyze color and composition. Radars probe beneath the crust. Magnetometers trace invisible fields. Together, they create a layered map of the planet's behavior across time and altitude. The result is not a single picture, but a moving portrait, a film of subtle change. Imagine looking at one of those composite images. Blue shades mark frost. Red marks dust. White streaks show clouds or storms. Over the course of a Martian year, the colors pulse, fading and returning like tides. The poles breathe in and out. Equatorial dunes migrate slightly. Shadows lengthen and shorten as the planet tips on its axis. It is a world alive in slow motion. In everyday language, the cartographers above have turned Mars into a clock, and its hands are made of light. The orbiters have also found hints of subsurface water that may still be liquid, trapped under layers of ice and dust. Radar echoes from certain regions behave differently, as if bouncing off a smooth surface rather than solid rock. Some researchers interpret this as evidence of brine, a salty liquid that remains unfrozen even in extreme cold. Others argue for dry explanations. But the possibility remains tantalizing. If true, these hidden pockets could be the last refuges of habitability on the planet. Why? It matters stretches beyond science to responsibility. If subsurface water exists, it could harbor ecosystems or be pristine environments we must not contaminate. The cartographer's data therefore guide not only exploration, but ethics. Each new map tells us where to send landers safely, where to drill, and where to stay away. The work of orbiters becomes a moral compass as much as a scientific one. Think of each satellite as a lighthouse rather than a spyglass. Its beams sweep the planet, not to conquer, but to warn and guide. They mark safe harbors for future missions, tracing paths for descent, mapping radiation levels, and locating resources. Without them, any landing would be guesswork. The orbiters transform Mars from an unknown wilderness into a readable landscape, one where every grain of dust has coordinates. Simply put, the cartographers above draw the maps that will one day decide who lives below. Their collective work also answers a deeper question about time. By watching the same features over decades, we learn how long change takes on another world. A dune that moves a few meters per year becomes a calendar. A fresh impact crater becomes a timestamp. The steady loss of air becomes a heartbeat. These measurements connect the short span of human missions to the long span of planetary evolution. At night, when the orbiters pass into darkness, their sensors keep recording. Infrared cameras track how quickly the ground cools, revealing which rocks retain heat and which lose it. The temperature maps tell us about density, grain size, and composition. Some surfaces glow warmer than expected, suggesting buried ice or recent activity. Even in darkness, Mars reveals new layers of meaning. Why do we persist in this watching? Because every new orbit completes another sentence in the language of understanding. Mars is no longer a mystery glimpsed through telescopes. It is a measured world, one that speaks through data. The cartographers are translators, turning energy and reflection into insight. In everyday language, they are teaching us to see with instruments instead of eyes. The greatest revelation from these orbiters is not any single map or discovery. It is the realization that Mars is connected to the rest of the solar system by invisible exchanges. It receives dust from comets, loses air to the sun, and sends grains back into space. Its climate, once thought to be self-contained, is part of a larger network of energy that flows between worlds. The cartographers above are not just mapping Mars, they are charting the conversation between a planet and its star. Why? It matters concludes here, By tracing that conversation, we glimpse our own future. The same processes that stripped Mars's air could one day influence Earth if our magnetic field weakens. The same solar storms that light up its skies brush our satellites and power grids. To study Mars from above is to study fragility from a safe distance, while the lesson still belongs to curiosity rather than survival. Soon, the focus of those orbiters will shift again. From mapping to support, they will watch as new missions attempt the first human landing, relaying signals, guiding trajectories, and confirming safety. The cartographers who once watched for science will become lifelines for explorers. Their maps of radiation, ice, and weather will decide where to build, where to hide, and where to dream. As they circle the planet, they transmit more than data. They transmit continuity. Each orbit reminds us that discovery is cumulative, that the story of Mars is written layer by layer, mission by mission. The eyes in the sky have shown us that to understand a world, one must see it from both within and above. And so, having charted the silent breath of the atmosphere and the frozen seas beneath, the gaze now turns toward the question of motion, not of dust or air, but of humans and machines. How do we cross the gulf between orbit and surface without losing our way? To answer that, we descend from the watchtowers in the sky to the engineers and dreamers below. Those who ask not only can we go, but can we come back? So we now turn to the question, can we actually go? Well, the question seems simple. We have mapped the planet, measured its air, tasted its water. We have machines circling it, rovers crawling on its surface, and rockets powerful enough to reach its orbit. Yet every time the idea of sending people to Mars moves from dream to plan, the numbers push back. Distance, mass, radiation, and time add up to a ledger that no optimism can erase. To ask if we can go is to open that ledger and read it line by line. The first line is distance. Mars is close enough to tempt us, and far enough to punish any mistake. The shortest route, a careful dance between orbits, still takes 6 to 9 months each way. At its nearest approach, the planet is about 55 million kilometers from Earth. At its farthest, more than 400 million. Communication signals, even traveling at the speed of light, take up to 20 minutes to cross that gap. There can be no instant correction, no quick rescue. Every maneuver must be planned, rehearsed, and left to unfold on its own. In plain terms, a crew bound for Mars would be more alone than any humans have ever been. The second line is radiation. Beyond Earth's magnetic field, space is not empty. It is filled with high-energy particles from the Sun and from distant stars. On the International Space Station, astronauts are still partly shielded by Earth's magnetosphere. A trip to Mars means exposure to levels of radiation that can damage cells, increase cancer risk, and degrade materials. To stay alive, travelers must live inside walls of water, plastic, or hydrogen-rich compounds that absorb charged particles. The thicker the protection, the heavier the ship, and the heavier the ship, the more fuel it needs. Every safeguard becomes another number in the freight ledger. Think of it like this. Safety adds weight, and weight adds danger. The third line is time. A round-trip mission would last at least 2 years. Crew members would spend most of that time in deep space or on a barren planet with only what they brought or made. Food must last or be grown. Machines must work flawlessly or be repaired with limited supplies. A single failure in life support, propulsion, or shielding could end the mission quietly and completely. The challenge is not only technological, but psychological. Isolation changes people. Even on Earth, long-duration missions in analog habitats show how small frictions can grow under confinement. A Martian crew would live in a pressure cooker of silence and necessity. Why it matters emerges clearly here. The hardest part of reaching Mars is not the launch. It is staying alive after the celebration. The next line of the ledger concerns fuel. Rockets must obey physics, and physics is ruthless. To carry enough propellant for a return trip from Mars, a spacecraft launched from Earth would need to be impossibly massive. The solution is to make fuel there. This idea, known as in situ resource utilization, relies on turning Martian air into methane and oxygen. Carbon dioxide dominates the atmosphere. Hydrogen can come from water ice. Combined through chemical reactions powered by solar or nuclear energy, they can produce the propellant needed for the flight home. Simply put, the return ticket must be printed on the planet itself. Experiments on Earth and aboard test missions have already demonstrated the chemistry. Small prototypes can split carbon dioxide into oxygen. The challenge is scaling it up. A real system must run for months, producing tons of gas with no human supervision. It must survive dust storms, temperature swings, and power fluctuations. If it fails before the crew arrives, there will be no way back. This dependency shifts risk from human endurance to machine reliability. Why does this risk feel different? Because it forces trust in systems that cannot fail quietly. Every mission design now includes redundancy, automation, and remote diagnostics. Engineers build triple backups for critical parts. Still, no test on Earth can replicate the wear and dust of Mars. Every valve and motor will face a world that grinds metal finer than powder. Radiation, time, and fuel are joined by another problem: gravity. Mars has only 38% of Earth's gravity, enough to keep people anchored but not enough to maintain long-term health. Muscles and bones weaken. Fluids shift. The return journey to Earth may take place in bodies that have forgotten their weight. Exercise regimes can help, but no one knows if partial gravity is safe for years. The first colonists will be test subjects whether they want to or not. In everyday language, going to Mars means rewriting what it means to be human in motion. Yet amid all these numbers, there is progress. New rockets capable of carrying heavy loads are nearing operational maturity. Reusable boosters have cut the cost of access to orbit. Advanced habitats are being tested for radiation shielding using simple materials like water and polyethylene. Robotic precursors could pre-build shelters and fuel plants years before humans launch. The pieces are falling into place, even if the final picture is not yet stable. Why? It matters broadens beyond survival. The act of preparing such a mission forces innovation that benefits Earth: lightweight power systems, closed-loop life support, and precision manufacturing in hostile environments all translate into technologies that can serve life here. The challenge of Mars is also a mirror of sustainability: how to live indefinitely with finite resources. Simply put, Mars is not just a destination, it is a rehearsal for responsibility. Still, ambition has a price measured not only in money but in ethics. Sending people to Mars means exposing them to risks that cannot be fully mitigated. Each volunteer accepts that rescue is unlikely. Each decision to proceed weighs courage against consequence. The question becomes whether exploration justifies the potential loss of life. History suggests it often has. But the scale of this venture magnifies the stakes. There is also the moral question of contamination. We have seen that water and chemistry exist on Mars, if life ever arose there. Even at the microbial level, our presence could erase it before we detect it. The first footprints on Mars might overwrite the oldest traces of another biology. International agreements demand sterilization, yet absolute purity is impossible. Every spacecraft carries microscopic stowaways. The debate is no longer if we will contaminate, but how much and whether we can ever undo it. Why does this tension persist? Because exploration and preservation pull in opposite directions. To learn, we must touch. To protect, we must refrain. Somewhere between those impulses lies the line that defines responsible discovery. To put it another way, Mars asks us to balance curiosity with humility. The economics of the mission deepen the complexity. Launching even one cargo of supplies to Mars costs billions. A self-sustaining presence would require dozens of such launches. Advocates argue that economies of scale and private investment will lower the cost, just as early railroads did. Critics reply that no frontier has ever paid for itself quickly. The truth likely lies in between. The first missions will be symbolic, not profitable. They will pave the way for an infrastructure that future generations might actually use. At the heart of this argument is the freight ledger. Every kilogram sent to Mars costs thousands of dollars. Each liter of water, each breath of oxygen, each tool and screw must earn its place. The arithmetic is cold, but it creates discipline. A mission that cannot justify its mass cannot leave the ground. In that sense, the physics of weight doubles as a philosophy of intention. Think of the logistics chain stretching from factory to launch pad to interplanetary space. It is a lifeline that must remain unbroken. Every launch window opens only once every 26 months when Earth and Mars align. Miss it, and you wait more than 2 years for the next chance. Time itself becomes cargo, precious and irreplaceable. Why? It matters peaks here. The effort to reach Mars reveals how finely tuned our civilization is. To send even a handful of people to another world, thousands must cooperate flawlessly across nations and disciplines. The mission becomes not a triumph of individuals, but of systems. In that sense, the journey to Mars is already underway, happening in labs, factories, and launch sites on Earth. In everyday language, we are building the bridge before we see the other shore. So, can we actually go? The answer is yes, but not cheaply, not safely, and not soon without risk. The technology exists in parts, the will exists in bursts, and the meaning of success remains open. If all goes well, the first footprints may appear within our lifetime. If not, they will still appear someday, carried by others who build on the groundwork of today. Simply put, we are close enough to believe and far enough to doubt. The question that follows is not whether we can go, but whether we should, and what kind of future we create by doing so. Do we travel for knowledge, for survival, or for expansion? Do we bring with us the same habits that threaten our homeworld, or do we learn from Mars's history of loss to build differently? Each rocket that rises from Earth carries not just fuel but philosophy. If the engines ignite, they will carry our hopes and our contradictions into the black. When they land, the first breath of recycled air under a Martian dome will mark the start of a new chapter in human story. But that chapter will only endure if the lessons of science guide it, not the appetite for conquest. And when that moment comes, when the first human looks up through a transparent roof and sees the stars at noon, they will remember the watchtowers that mapped the way. Those cartographers above taught us how to navigate, but they could not tell us why. The answer must come from within, as we step from machines to meaning. We have reached the limit of preparation. The next horizon is not technological but philosophical. Before we take that step, we must ask what it will mean for us as a species to multiply worlds. For that, we will need to leave the tools behind and turn to reflection. So we now step into the echo that follows discovery and enter the final act, the philosophical echo. Every voyage ends where meaning begins. The maps are complete, the engines silent, the numbers tallied. What remains is the echo of what it all meant. Mars has become more than a destination. It is a mirror, and in its reflection we see both our reach and our restraint. The story we have told across the last chapters is not only about a planet, it is about a species that cannot stop asking what lies beyond its horizon, even when the horizon leads into peril. Imagine, for a moment, the first human standing on Martian soil. The dust is still settling around their boots. The sky is pale orange. The sun a distant ember. Behind them, Earth hangs as a blue dot barely larger than a coin. In that instant, all of human history collapses into one image. Every invention, every failure, every question has led to this: a person breathing borrowed air, under an alien sky, aware of the fragility of both. In plain terms, we have left home to understand what home truly is. The silence of Mars is unlike any silence on Earth. It has never known birds, waves, or trees. The wind has no leaves to stir, no seas to carry. It is a silence without memory. When we bring our presence into it, We change that silence forever. We add footsteps, signals, traces of heat, and the steady hum of machinery. We might call this progress, but it is also intrusion. For the first time, the planet will carry a sound that did not come from itself. Why? It Matters unfolds beyond science. The search for life on Mars has always doubled as a search for our own moral boundaries. If we find even a microbe in that frozen soil, we will face a decision with no precedent. Do we protect it, knowing that protection may limit our future there? Or do we proceed, knowing that our survival might erase the only other biology we have ever found? The question is not technical, it is ethical. Think of it like this: the moment we confirm we are not alone, we will have to decide what kind of neighbor we intend to be. If Mars is lifeless, the moral question does not vanish. It shifts. A dead world is not a blank one. It is a record of failures and possibilities. Terraforming a word that once sounded noble becomes an act of rewriting history. To make Mars more Earth-like is to destroy the conditions that made it Mars. We would trade a museum of planetary evolution for a new suburb of our own design. Whether that is progress or vandalism depends entirely on why we do it. Simply put, colonization without reflection is only repetition in a different color. The deeper lesson of Mars is humility. We tend to imagine ourselves as exceptional, capable of mastering environments by force of will. But Mars resists mastery. Its cold, its dryness, its distance remind us that nature does not negotiate. Every plan we make must conform to its physics. Every step must respect its scarcity. To live there, even for a day, would require dependence on systems we barely understand and on each other more than ever before. Why it matters becomes personal here. The pursuit of another world is also a test of who we are together. Will the first Martian base be a symbol of unity or competition? Will we share data freely? Or will we claim the ground beneath our flags? History whispers both possibilities. The Cold War gave us the moon. Cooperation gave us the space station. Mars could follow either path. The planet itself will not care, but the meaning we draw from it will depend on the choices we make. In everyday language, Mars will show us what kind of civilization we have become. There is another echo that runs deeper still. For centuries, humanity looked up at the sky and imagined gods, then worlds, then neighbors. Each layer of discovery stripped away illusion, but left wonder intact. Now, as our machines read the chemical breath of another planet, the line between science and philosophy blurs. To study Mars is to study the conditions that made us possible. Its loss of atmosphere, its frozen rivers, its magnetic silence are all versions of what could one day happen here. If the cosmos keeps records, Mars is one of its cautionary entries. Some have argued that spreading life beyond Earth is our duty, a way to ensure that intelligence survives if disaster strikes home. Others counter that we have no right to export our contradictions until we have resolved them. Both views share the same truth. Survival is not enough. What matters is the quality of what survives. A human presence on Mars will mean nothing if it carries the same carelessness that eroded our own planet's balance. To put it another way, every footprint on Mars will echo back into the ethics of Earth. The question of contact, the one that began this entire exploration, returns here in a new form. The dark forest theory warns that communication across civilizations might be dangerous because silence can mean survival. Mars poses a quieter version of that riddle. Do we speak first, by transforming it into our image, or do we listen longer, hoping to hear something faint but original? The answer may decide not only what we find, but who we become. At the same time, Mars offers a chance for redemption. If we can learn to build a sustainable society in an environment that gives us nothing for free, then perhaps we can learn to preserve our own planet better. A habitat that wastes even a drop of air will fail. A culture that ignores balance will perish. The lessons of survival on Mars are the same lessons we ignore on Earth, written in harsher ink. Why it matters reaches its final form here. The effort to reach Mars is not about escape, it is about perspective. By standing on another world, we might finally see our own as unique. The red planet is a mirror, and the reflection it offers is both beautiful and unforgiving. It shows a species capable of building miracles and repeating mistakes. The reflection asks if wisdom can travel as far as technology. Simply put, the true journey to Mars begins inside us. The silence returns. The explorer on the plane looks up at the faint light of Earth. The instruments have gone quiet, their data stored, their batteries fading. The only movement is the slow drift of dust over footprints that will last for centuries. There is no applause, no audience, only the distant heartbeat of the sun. In that emptiness lies a strange peace. The planet does not resist us, and it does not welcome us. It simply exists, waiting to see what kind of story we will write upon it. If we listen carefully, we may hear the faintest echo, not from the sky, but from within. It says that exploration was never about distance. It was about the courage to face the unknown and the humility to remain changed by it. The quiet of Mars teaches both lessons without speaking. We will continue to look outward because that is what we are built to do. But the true measure of discovery will always be how it changes the way we see home. The universe has given us a vast stage, yet every performance is watched by the same unblinking stars. And so we end where we began, with a question that refuses to settle if we find another world and reshape it to our will. Will we still recognize ourselves in the mirror of its sky? Or will we become something entirely new?